Hi everybody. Hi Eduardo. Really happy to see you today. We are going to start that live, and I really hope we are going to see other stuff in Core Lightning implementation, and maybe we will have some fun. And today we are going to code a little bit in comparison to the last session where we read a lot. But still, we are going to also read a little bit today. So what we are doing in that series about multi-event invoices is that we try to understand how the multi-event protocol is part of the protocol is implemented inside of Core Lightning, and we take that opportunity to try to understand a little bit more how to navigate in the code. So the first series we've seen how to add command in Lightning D. In the second session, if I remember well, we've seen how to log sentences, lines in the log files. So two things that we might want to do. And today we are going to look at beg32 encoding. So this is encoded chosen by Bolt 11 to encode the information about an invoice, and at some point we need to do that step to get that string which encode all the information. So we are going today to look specifically just at that part of the code that is implemented in and we can see there in the files command in the subdirectory command called beg32.c, and we also are going to see that this is just a copy and paste with just a little changes on the size of the string we output that come from the implementation given in the BIP 173. So how can we do that such that we do stuff directly? So as I do, I think when we do the live, I jump into the code and we see what we can get as information, and we try to write some stuff. And if it works, great. If it doesn't work, we will read the error code, and I hope we get a better understanding and we get something working. So we can see at the top we have Bolt 11 invoice cut in 4 parts, and we can where we have the first part that is called the human readable part, and there are some information in it, like the chain we are working on. So this one is for Lightning and the reg test, and we have the amount, N is for nano compared to the Bitcoin. We have a separator, and the separator is the last number one in the Bolt 11 string. And this is always the case in beg32 encoding. So this is the separator. Then we have some data, and still we haven't looked so far at how that data is encoded here. We've seen that yes, at some point we might want to encode the root ints. So we look at that last time. The first part of that data part encode the timestamp, but we this is not what we care about right now. This is just that we have that data, and that data uses a specific alphabet of 30 characters that are described in BIP 173. And at the end, which is also specified by that BIP, we have a checksum that is well chosen by BIP 173. And before we continue, so there's some links. So as always, there will be I will provide on lnroom.live all the information on the link. And so this GitHub SIPA Bake32, there are many implementation of Bake32. So the one also used in Core Lightning. We have the BIP 173 and also one video that if you have some time to listen to Peter Will that explain. He's the author and co-author of BIP 173, and it explains how they choose the checksum at the end that allow to do error detection. Not in every cases, but in some cases. So this is really interesting. I must admit that I didn't understand. I understand just a few parts, but anyway, it's interesting to see why we might want to do that way on the work needed to end up with a code detection code of error that works in the cases that they've showed, and let's say better that you watch the video if you are interested. So let's go into we're going into the code so that I will feel better. So as usual, we have a Lightning repository here. I'm checked out at release 23.11, and what we want to go is common, and let's go in the directory common, and that directory is interesting, and we can see it at the library for Lightning. So I think that if any of those library, those .h file there can be used in another part. So this is interesting because if you want to write a plugin in C, either outside of Lightning or in Lightning, you have access to all those library, and they are tested with Lightning. So this is a big advantage. And we see here we have the Bake32 files. So let's go in the. Yes, we can look at both. So there are two functions that we. No, sorry. So not base33, but Bake32, and we see at the top that this is stolen from a SIPA Bake32 repository by Peter Will, and we see that in BIP 173, the max size of the encoded string is must be inferior to 90, but in Lightning this is not the case. So there are some place in the code where that change. This is the only difference between the two code, because in that so if we go back in on or not in that data part, we might want to have many information, not only the amount, but description, root hints, and other stuff that we put there. So the string can be way larger than the 90 character authorized in 173 BIP. So we have those functions, and we have one which is that one Bake32 encode. So we are going to try to use that function just to see how to use it, because to understand the overall of the implementation of the function of the command invoice in Core Lightning, at some point we encode something and we use that function. So we can see that we pass it in the output. This is what we. This is where we put the encoded string. What else? So we have we give it the human readable part, HRP, and also we pass it the data, and that data is an array of all the, how to say that. So when we've decided how we the data that we have, how it is represented, we transform it into how to say that. We transform it into an array of. So we have it here. So an array of 5-bit values, which is beg32. There's 2 to 5. 2 power 5 choice. So we transform those information into an array of 5-bit, and those 5 bits are given to beg32 encoded, and using the alphabet of beg32 to transform that thing. So we are going to look at that, and one thing that changed is the max output length. This one. That doesn't exist in the implementation of SIPA beg32 because it's hard-coded to 90. But this is not our case, so maybe we can just read this here. But if you want, why I say that is because if you want to see more example or test of beg32 encoded, there are more tests in the SIPA beg32 repository. So it's just for that matter that I mentioned that. So beg32 and the implementation is here. And better than looking at we are going to look at the implementation, but I think that's better to run some code and go back to the node. And in the BIP 183, the alphabet. So let's look a little bit at that first. The human readable part can be ASCII character one, at least one, and this must be the value between 33 to 126. So what does that mean? So if we look at the ASCII man page. This is ASCII man page. So we can see this is 127 character ASCII character, and the first one are not printable, so we can see in decimal. So on that column, so 1, 2, 3. So we have the new character. We go down, and the 32 yes is the space, and then we start with the 33. So we from 33, which is the exclamation, we go down, and we can go to the last one, which is a tilde. So we can see here, which is 126. So this is what is said there. We can use all of the characters in the human readable part. Then we have the separator one, and the beg32 character set is the alphanumeric character, so 0 to 9, lowercase a to d, but those one. And I think that there is an explanation why they dismissed those one, but we are not going to look at that. So that table tells us that when we get the data and we transform it into a number from 0 to 31, then to encode it with bake32, we do that with that table. So 0 will be Q. Okay, 1 will be P, 2 will be transformed into Z, and we go on and on. And for instance, if we go at the second line, 2 will be encoded. 10 will be encoded with 2. So this is what is done. And if we go back to bake32, that one, this is what we see here. So we have the car set to go from 0 to 20, 0 to 31 to all of those characters. So we can see here we have a Q, P, Z, R, so on and on up to the end, and to go back in a reverse order. So if given a number that represents the character, so for instance, this one, we see, so this is for the its number in that array lead to 50. So let's go back and to the ASCII character, and we see if we go, we have the 38, and this will go to the value 0. So we see here 0, it at the 15th position, I think. Okay, so we are in the common directory. We have the function that encode that will use those character sets. Let's fire a terminal, and we are in the Lightning repository. And as we want to, we are going to configure what the makefiles, the variable for the makefiles, and we disable Rust because we don't use it. And after we are going to compile. And one interesting thing is that when we want to try things out with those library in the common directory or do other stuff, we might not need to run Lightning and to do to pay an invoice or to do something. Maybe we would just want to check one function in one library, and this is what we're going to see by running the test. So we are here now. We compiled it. So we are in the buffer that compiled this, and we see I just run make -j4 to compile this. So as this is the first time, it will compile everything. After, when we make changes, we are not not going to need to recompile everything. And let's go. So we are in the common directory, and maybe we can go into the makefiles. Okay, so that makefiles. So when we compile, we have that makefiles that is included. We see at the end that will also include the makefile in the test directory. So there are unit tests that are just small programs that we can run individually. So we are going to run Bolt 11. Why Bolt 11? It's because this is we try to understand Bolt 11. And we try to understand bake32, so maybe it's already used in that file. So why not just using that file? We are going to compile it and to see that we can test things that way. So in the test, we see we go in the makefiles of the subdirectory test, and we see at the top that the common test source variable is set to all the files that start by run dash something and that end with .c. So we can see them here, and all those files get compiled, and we can run them. So right now it doesn't seem to let's go here. Okay, so the compilation it's not done yet, but normally at some point here we are going to see the binary files there. And let's go to run -bolt 11, and we are going to use that one, to compile that one, and to play with that, because we see at the top. So we are using at least, maybe we are not. I think we use it once in that test, but at least we import that library, so we can just compile that file and play with the function in it. So this defines something, how to test all the data of the bolt 11 inside. And at the end, we have a main function that does the test of this one specifically, as it must comply with bolt 11 bolt 11 part of the protocol. All those things that we see here that we are testing are in the bolt repository. So because these are the test vectors that are there, and we see at some point we do some stuff, and let's look if we have an assert somewhere. So we have a bunch of assertion where we try to test to see if it works. So we can throw away those things and do. We are not going to use assert, but just print stuff out today. But let's go back to the compilation. Still not done. Okay. It take a little bit of time. My computer is not super fast. Maybe I should say it is slow. Let me take a little break. Drink some water. Okay, so the compilation is finished. It seems that everything is working correctly. Now you can see at the bottom. Let's go to the terminal. And what we've done so far in every live and videos in LN Room is that we were starting a few nodes running on reg test chain, and we were trying this out with the RPC command offered by LightningD. And today we don't do that. So we can run those individual tests. And for instance, we can run bolt 11 as we change nothing. This should just work on return something that works. So it works if we break it. But let's okay. As I'm saying that we can break it, maybe here instead of bake32, I'm anywhere in the file. We don't care. But as we are in an asset stuff, we can do something like that. So maybe back a bad back. We compile again. So there's a bunch of stuff that are going to recompile. Way less that before. And we're going to see that this fails, and the assets will tell us where we failed. It's not precise. We don't get the line where we failed, but we get some information that it failed. Just to see that this is one way we can have to play with some part of Lightning without having to run the daemon and play with the daemon on maybe log stuff to understand what's going on, because we don't want to see those stuff. What we want to do today is just I would like just to use those two functions and see where they are used in the code, take the part where they are used, transform it a little bit to have an example, and then find a way to generate not a Bolt 11 compliant string, because the data need to have a special shape, but someone with a human visible part, a separator, some data that we relate to that alphabet and that character set and those things. So let's go back to the compilation. So I don't know why it is recompiling so much stuff. Maybe at some point it don't do that. If you know why is that, Eduardo, you can tell me, but I don't know. When I was playing with that before, it was not recompiling all of those things. But okay, so while we are doing that, let's go back in the directory test, and what we want to do is to copy run Bolt 11. So compilation finish. We're going to see that. No, let's go back into the terminal, and we see that we don't get an error. But we change the file. Okay, let's me. Did I save? Yes, I saved something. I'm not happy with that because I really. Okay, so let's do it in another place. Okay, it would be great to just see that if we change something here and it's wrong. Okay, let's try with okay. Here we have a timestamp. Maybe we are just going to change it, and if we change it with 2.0, so we do that again. So let's see what we get. Okay, so this is what I was telling you before. I don't know why right now it doesn't recompile everything that it did before. So let's go back to the terminal. So now it can be faster. Okay, so this is what I wanted. So we see that we've changed something, and while we were running that file at line 60, we have an error with an assertion that have to do with the timestamp. We know where we did the error, so we are just going to go back to the right one, and in fact we don't care about that. But just this is something. So right now, if we want to test, understand how the B11 is struct is implemented and works, there we can play with that. But this is not the thing. Let's copy. So we copy run Bolt 11 into something that we are going to bake 32. And we are going to try some things. We have it here, and as it starts with run dash something, we remember that in the make files of the test at the top, we know that that file is going to be compiled. So let's do that. It compiled again. Anyway, so it compiled that. Maybe after, as we will have that file, this won't be compiled again. So let's go back into our test directory, into bec32. We are there. We wait that to the repository to be compiled, of the files in the repository, and then we are going to modify it. Maybe we can bec32. So we in .c, and how it is where this is used. So we do a grep in the repository to see where bec32 encode is used, and we see we don't have many places where it is used, and the place that we are interested in will be that one. So in Bolt 11, we see how it is used. So let's jump into that file. So we are in the file command/bolt 11.c. So you can see that at the bottom of the screen in that bottom line. So this is where this is used, and we see the name of that function. This is a function bolt 11 encode. So at some point, we build some information here that in the struct of bolt 11. So this is done somewhere, and we just assume that now we want to encode that function. We see that we start at the beginning with an array, an empty array of U5. So U5 is to say inside a car of size 5, but in fact we can jump into that definition. We see that this is an inside car. So it will take if I'm not wrong, yes, it takes 1 byte, so 8 bits of size, but calling it U5, we understand what we want to do. So this is my understanding. I hope I'm not telling wrong things. So, but it's an inside car. So we go from 0 to only positive number. So let's go back. So we have that data, and that data is really, so we go back to our note. So please tell me. So hi Drew. So please tell me if I'm jumping back and forth between the screen too fast. I will slow down. But let's continue. If we see that thing, in that we have that data part that we want to encode with bec32 characters. So one part of the code here is really to take the information that we have in the B11 that we get from somewhere. Okay. We build that array with which is an array of U5s and with value comprised between 0 to 31. So this is 32 value, so the 2 to power 5. And with those things, so that data, where we do those stuff. So at some point in the next session, we will look at some of them. To see what is happening, and at the end, so the output is just a string with the right allocation, and this is what we return. This is the encoded string with all the information on the end, which is a checksum. So this is done, and we do that at that moment. So bec32 encode, and what I wanted to say is that part. So we have the human readable part, and we pass it the data. And in bec32 encode, so we can jump to it. This is where we do the job. but let's better use it. So I don't remember why we were compiling something, no? If I'm not wrong. So we compiled because we've created a new file called run-bec32, and that file didn't existed before, and this is the exact same files of run bolt 11. So it will we should see it here, and no output is just to say that everything works well, and this is normal because this is exactly the run bolt 11 file. So let's go back to bec33. Now this is run bec33. So we are in that file. And now we are going to remove. So I don't know how people program, but this is how I used to work in a repository. Just I pick stuff somewhere, I put that in another place. I try things up. I look for how function are called. I copy and paste some of the stuff, and at the end we get something that we want. So we are going to remove that helper that was used to test the function. We don't need that. We don't need the private key, neither those one. So we are with that. We don't care of the include files. It's not our business because we just want to try things up. So printf, it seems, I think it is loaded somewhere before, so it should work. And we compile again. Okay, so let's go back to the terminal, and we see we have foo. But it's not. I think you see it. I should have put a new line. So now we have the 35 minutes to just print it through. But anyway, I think we've looked at some stuff to get there. But just that when we do that, this is some way that if we want to try something out, no need to build a little replication stuff program somewhere else with a dedicated make files to try. If, let's say you want to understand some of the CCAN library used inside. You don't need to do it somewhere else. You just add a file in that test directory. You import CCAN, and we import CCAN, and we try those things. So now let's see if we can use that encoding. So as I was telling you before, I used to work like that. So now we go to run. What do we want? We passed that, and at some point we need to declare the output. So we are going to go there. Output is declared somewhere here. We have the output, the RShape, so that are strings. Let's take those one. We go back here. So we have that, and just one thing. So this is the way to free those stuff, but we are not doing something clean. This is not what we need to do at that point. So bec32, it's an enum, so we go there's one of those three things. So if we need to, when we return that we won't able to encode something. So it's just something defined somewhere. The output. So we have to do that. Now we want to print out the output. The output, this is that string. maybe we should give some explanation. So, blah blah blah. Sorry. Here we do that because when we use tal r, what's cool is that we can use tal count, which is here, to give us the length of the array. Okay, so this is interesting when on needed in the case where it is used in volt element underscore encode underscore, I think the name of the function, but as we are testing, we don't need to specify to do this, that as we don't know the length of the field. So we still want the data encoded with number between 0 to 31, but this is an array that we can specify directly. So I want to do that like that. So an array of three characters, and we want 0, 1, 0. We can use other. We don't have to use them to use those one, but I want to do it that way. So we know the size. The size is 3. So in that part, we are going to keep that line commented. Okay, so this is 3. Maybe I should talk about tal r. So this is a function that declare and will also. It's not only that it declares; it allocates a memory from a context that we have here. That context were well defined in the other function. We are going to see the one that we can use when we need some context to which is of type tal underscore t. This is an array of character, and then the last part, that one is the length, and we see how we calculate that length. This is the total length of the string encoded, the encoded string with Beck 32 encoded, so that we've seen blah blah blah. So let's go back to our note. This is that total length that we have to pass. So we are summing number there that told us what they are. And so 3, we know where that comes from. Okay, so 3, this is the length of the data. Okay, so that means that if we go back in here, we are going to have three value. And if you're okay with me, what we've been using in that array, so maybe can we have it here? Yes, maybe that way. So side by side, so we see we have that array, and on the right 0, 1, 0, and so we are going to have in the string Q, P, and Q. Okay, normally if I understand correctly and everything works and I'm not lying, I hope this is what we're doing. So this is the 3. Now HRP is the length of the human readable part. So the human readable part is a string. Maybe we can just pass it, define it like that. So if I'm not wrong, how can we do that? So let's use that one. Okay, so that human readable part, we use it directly in Beck 32 encode, human readable part, and the number of characters we see at the bottom, there are 10. So now 10 is for that, and we no longer need that one. So we really are doing hard-coded stuff with things to, like, how to say that, to not deal with how maybe I'm even if it seems easy or simple. I always prefer to when we use variable is really when we need it, when we abstract something on where we want to be to help the reader to understand what is it what we are doing too also. And there's another. I was thinking about another thing, but when we are trying things like that, I prefer to do this like that. Now we still have to do the context right, but let's talk about that last one. So 8. Why 8 at that length? So this is we look correctly at the note, we see that we have already counted that part. We can't also counted the data part. We need 6 for the checksum, 1 for the separator, so this is 7, and why 8? Why we are missing 1? It's because just we are with C, and we want the C programming language, so we want to end the string with 0, so that we can use it without knowing its length after. So in the output, so we want the output to end with 0. So we need to pass it that number, and we can see that if we go into the bake32 encode, so we do some stuff. We are looking at some stuff, blah blah blah. And we are building the output. Huh? So each time we see outputs, this is what we are doing. And we see at the end, okay, at the end of the output where we are, we put the value where the pointer is. We put the value 0. So we are almost done, but we need to have some context. So this is what I was telling you. So we can use a temporary context that is defined in the util in command underscore slash utils.c, and each time we need that that pointer to tal t, we can use that like this. We are almost there. So we talk. Tal count of data. So the data, they are free, the length, and this is the maximum size t-1. This is the maximum size that we want. If we were to use bake32 in another context than here, so with SIPA bake32, that size is not an argument of that function and is 90. But we talked about that before. Sorry, I don't know what I did. So now let's compile it. So let's go back to run. I think we look at that. So I talked a lot and see that I made a mistake. Now, why don't we have something? Okay, so okay, so yeah, so what was wrong? So if in any case, if I really don't see how to do it correctly, I have a cheat sheet in my in the note. Sorry, there is some question. Okay, thank you. Yes. No, thank you, Eduardo. Okay, so maybe there are better way to do something. So I'm just reading what Eduardo is mentioning. If you look at other, so Tony, if you look at other test files, you will notice in the main at first line that calls command setup, and at the end a call to command shutdown. The first is needed to allocate temporary context. Okay, so okay, let's just I will do that just after. But first, you're right. There is something wrong with the pointer, and if we have the error that you are mentioning, I will add the command setup. Thank you for mentioning it. Okay, terminal, and now we see that. So I will just copy paste what you told me, so that we have it, and people can try this out. So note, we go to the note. So one comment from Eduardo was this one. So in other test files, so we use command setup and command shutdown to allocate a temporary context. So right now, I don't know why, but it seems command setup argv0. Okay. Thanks, Eduardo, to help me out with those things. So it seems that we don't need it right now. So I won't add it right now to the field, but I will look at that after and make a comment in the transcript to count with that thing. So we can see now we get that what we wanted. So we have that part. We have the separator, and we have the data field Q, PQ, and then at the end, this is the last part that, not the last part, but this is the checksum. Okay, cool. Okay, maybe we have 5 minutes left to end that session, but I wanted to like, it's not that much what we did today, but anyway, I hope this is anyway helpful. Okay, so better than decoding that things. The decoding, I will have it in the transcript, but we can just with those last 5 minutes look at bake32 encoding. So that function. So rapidly. So we have the output. This is the output that we want to construct. We have the human readable part and the data that is transformed at some point into a character from a number from 0 to 31 that are encoded at the end. We see here the check for the characters between 33 and 126 that we've seen before. Then there's another check. This one is for we don't want mixed case in bake32 encoded string, and I think so. How they are uppercase, this is just for QR code is better. How they are lowercase, and I think that when we encode and decode, they must be lowercase. So if we have something like that in the human readable part, this throw away. Each time we have a new character. This is the way the checksum is computed. So really, I absolutely don't understand nothing about that part, and I think it's require some prerequisites that I don't have to understand not only what's written, but why this is why does this work and allow to do error detection. So we continue. We are building here that line. It just checked the length of everything, and if we are not in Lightning but in other Bitcoin world and with the other implementation, max output length will be 90 at that point. So we continue to do those things, and we see here. So this is. Yes, so we set the value we incrementally set the value of pointing of output, and we increment it. When we are done with the HRP part, we put a parameter, the separator 1, and now we continue with the data part, doing the construction of the checksum, and we see here what we do is that with the value of the data at that moment we are looking at, we point at, this is a number between 0 to 31, and we do a lookup in beg32 set that we've seen, and in our case we passed 0 and 1, and this is why we get QP on the Q, and then we have the part with the checksum that is done, and this is set at that point in the output string, and the last one that comes to the null terminated string. So that's all that I have for you and for me today. I really hope this was useful. So thank you, Eduardo and Drew, to be there, and thank you for the questions. I didn't see the U5s, and I will look also at what you're saying, the command setup. So yes. Yes, so Eduardo says that checksum part is very complicated. Yes, I totally agree. So, but the video, so the video by Peter Twill is really. So I will post it. But it's really interesting to look at, to watch. Even if I didn't understand nothing, but yeah. So we are done for today. Thank you both to be there, and we see in 2 weeks to continue our journey into Bolt 11 implementation in Core Lightning. Yes, Happy New Year and Merry Christmas to guys. Okay, Eduardo, I post the link right now, so that if I take some time to write the transcript, so tell me when you've copied the link, and I will close the stream. Cool, perfect. So see you in 2 weeks. Have a good time.